This is Unit 11 for the AP Physics C exam review. We're going to look at electric circuits. Our most basic, electric circuit is, you take a battery, which we usually draw with these two lines, right? A positive terminal, negative terminal being the smaller one, and then, you could add two more if you want. And, we'll connect it to something like a light bulb, I don't know, and then, hey, the light bulb, it'll glow or something. I think that's what they do. And yeah, this is our most basic circuit. But what really is a circuit? Well, circuit needs current, right? Current that can start at one end of the terminal and then head all the way back. If I, cut the wire, that's what it is. If I cut the wire, current will no longer be able to reach back. And you won't get a complete circuit. This light bulb won't glow. Well, hey, what is current? Well, current is really just moving electrons. So electrons, wait, did I say moving? Oh, it's really moving charge, right? I'm saying there's charge moving from positive to negative. Really, it's the electrons, right? It's the negative charge going the other way. But I think Benjamin Franklin thought positives were moving, so now we use a conventional current that says that, hey, positives are the one moving, but it's, it works out the same if you were to have negatives going the other way. Current is moving charge, right? If charge moves, you have current. And current specifically is defined as the change in charge over the change in time, right? So the change in charge, right? If you were to look at this spot right here, right? It's like how much charge is here and how much charge is passing through that point. At what rate, I guess, does charge pass through this point, right? With respect to time. So you can imagine that, hey, that means, if current is a derivative of charge with respect to time, charge is really the integral of current with, integrating with time. So maybe you have a function of charge and you want to find out the current, right? You can take the derivative of that function, right? Let's say charge increases somehow, which you will see for a circuit like this, it wouldn't be true, but for whatever reason, if the current is, or if the charge is increasing, is changing, or let's say charge at this point is like 2t cubed, right? You can take the derivative to find current, and then if you're given current, you can find, you can integrate it with t1 to t2 to find the total charge that has passed through that point. So now let's talk about light bulbs, right? How do they glow? Well, a light bulb is really a resistor. That's actually what a light bulb is. A resistor is really anything that resists the flow of charge. That's kind of a dumb way to put it. A resistor is an element or something, like a device. An element's kind of that's a fancy word. It's just something that uses electrical energy, right? So, you have charge, right? You have charge, and we use positives moving, and they start at a high potential, and they go to a low potential. So they're having a change in potential difference from high to low, and if you think about, well, this electron is going to go from high to low potential. So the change, I'm saying electron, my fault, really the charge, right? So the change in energy for this charge is going to equal Q times change in V, where change in V is just the battery voltage. And sometimes we call this the EMF because, well, actually, I'll talk about EMF in this, like why it gets that name. But, well, hey, conservation of energy tells us that charge can't just lose energy out of nowhere, right? So if it's going through this potential difference, where does that energy go? Well, this resistor uses that energy. So this energy goes into the resistor. So the change in E of the charge is going to equal the change in E for the resistor, right? or I guess we can say energy used by a resistor. And I won't even call it change. I'll just call it like the energy, I guess, right? The energy of the charge is going to equal the energy of the resistor. And if this is equal to Q times change in V, right, this relationship is true. But this is not really helpful. This is not like, the reason, this isn't a helpful equation because oftentimes we don't know the charge, right? Like we don't know the amount of charge that's, passing through a resistor or going through a circuit. Like that's not really clear. So rather we like looking at rates, right? We don't know really the charge, but we know the current. And we'll talk about how we can find the current, but you can use a device like an ammeter or an ammeter. So and that measures current. So if you know the current, well, I can just take the derivative, right? This is not good notation, but I don't really feel like, you're taking the derivative of both of these. Well, the derivative of energy with respect to time is power, and the voltage of the battery isn't changing with respect to time, but the charge is. And dq dt is just current, right? We talked about that. So the power of the rate at which the resistor dissipates energy is given by I times V. Now, let's talk about one of the most, I guess, important-ish equations. Now, I guess I bet electrical engineers actually probably disagree with this, but at least in AP Physics C, one of the most important equations is current, right? How do I find current? Well, it's going to be your voltage over the resistance. Hey, that's Ohm's law. That's what we call Ohm's law. It tells us that, hey, current is proportional to the voltage, and for a certain circuit, the amount of current you get is just equal to the battery voltage over the total resistance, which is a cool relationship to have, right? If I were to graph I versus R, I versus V, the slope would be the inverse of the resistance, right? So that's an important, relationship to know, and yeah, this is Ohm's law, and it kind of tells us also that the resistance is unaffected by the voltage or the current, right? The resistance is really like a physical property. Well, yeah, it is a physical property of the resistor, and that isn't determined by the current or the voltage. In reality, your resistance does actually change. It does change, right? It does change with temperature and with you can get more resistance with hotter temperatures, I believe, and when you have higher voltages, that leads to high temperatures. So really, with really high voltages, your resistance gets kind of high. So you actually get a graph that ends up looking like this, right? With high voltages, as you keep increasing the voltage, you don't get the same change in I because your resistance is so high. The reciprocal of that is the slope. That's what we call a non-ohmic resistor. I don't think AP Physics C really deals with non-ohmic resistors that much, but just understand them, right? Understand what makes a resistor ohmic or non-ohmic. You'll see this equation in the form V equals change in V, right? The voltage is equal to I times R. So this is the top equation, more like conceptual, right? Change in V affects the I, right? Voltage is not affected by the resistance, right? If I double the resistance, I'm not doubling the change in V. That's fixed, right? That's a battery. Really what happens if I double R, my change in V is constant, I get half the voltage, right? That's how resistors, right? They resist the flow of current. If I have a high resistance, there's going to be a low current. It's trying to resist that. Why exactly it does that, I need to read more about that. The idea being, well, for when you have, regardless of your resistance, the charge is going through the same potential difference, i.e. the same, change in energy. So the energy dissipated needs to be the same. The rate at which it dissipates energy needs to be the same. So if I have I guess I should derive this first. Okay, how do I explain this? So V is the same. So if I increase R, there would be a greater, okay, I guess it's easier if I derive the equation. Well, what you notice is like, hey, change in V, right? I can just plug that into there. This is change in V, by the way. I use them interchangeably, so I'm sorry about that. But I get I times IR, or I squared times R. So if I increase the resistance, power needs to stay the same, so I goes down. But conceptually, it's like, well, if I increase the resistance, there would be bigger potential drops across the resistor. So the current would have to go down in order for conservation of energy to hold. You can also plug I into here, and you get another equation, P equals V squared times R. And we're going to see why these different forms are useful. First, really quickly, let's talk about our series and parallel rules. So similar to capacitors, by the way, I cover capacitors in the Unit 10 video, but if you have two resistors in series, right, connected to a battery, R1, R2, well, hey, they're going to have the same current. They will not have different currents. Reason being, current really is caused by charges moving, and those will, I guess, maybe, actually, no, I'll read more about it and explain why. But the idea being is, well, yeah, if current, current here, if it's really fast and the current here is really slow, then the electrons moving, right, which really go this way, they're going to start colliding with each other, and then I guess the electrons that are kind of slow kind of speed up. So I guess it's kind of like walking the halls, right? It's not like people walk different speeds, because as soon as one person walks a different speed, the others start like matching with that, so there's no chaos in the hallways. If that kind of makes sense. Same current. Resistors do not use up current, right? What they do is use up potential. The charge here is at a high potential, so it drops down one resistor, and then it drops down the other, and then it's back. Once it goes back to the battery, it's back to where it started. And that's an introduction to loop rule, but we'll get there. Same current. So I know that, well, these potential drops have to be the same as I kind of explained, right? It needs to, battery, so it starts here, increased by the battery, and then it drops 1, and then drops 2, and then it ends back to the same potential that it started with, right? If it had more potential or less potential, conservation of energy is violated. So the total battery EMF is going to equal change in V1 plus change in V2. Change in V1, well, that's just current times R1, and then current times R2 for the second voltage drop. I can factor out a current equals EMF, right? Well, if I divide both sides by I, well, the total voltage over the total current, that's just the effect or equivalent resistance, right? If you were to substitute these two resistors out for an equivalent resistor that would have the same current, well, that equivalent resistor would need to have the sum of the two resistors in resistance, right? And this applies for R3 plus R4, right? It's going to be the sum, I forget the notation, it's going to be the sum of each individual resistor. For parallel, right? For parallel, if I had two resistors in parallel, kind of back to what I was talking about in the last with capacitors, right? The voltage across each resistor has to be the same, because if I had charge here that goes up the battery potential and then drops down, let's say like the battery's 10 volts, right? So it's plus 10 volts, starts at 0, let's say, and then it goes plus 10 volts. If this one only did like 8 volts and this one did 10 volts, well, some charge will be at 10 volts, and then some charge will be at 8 volts. That violates conservation of energy, right? Because now you have some charge that's at a higher potential than others, which is weird. All the charge should be at the same potential. You would get some weird, crazy physics stuff if that wasn't the case, because charge goes from high to low potential. I don't know. I don't want to think about it, because that's just such a perplexed idea. Each voltage would be the same. It would equal the battery. But now, what changes is the current, right? Whatever your initial total current is, it actually splits from I1 into I2. And hopefully conceptually this makes sense. We'll explain this with Kirchhoff's laws. But the initial current here is the sum of the two, right? Conservation of charge, right? Where the charge splits, the total would, if you sum them up, it would just equal the initial. So the current initial will equal the sum of these currents. So in that case, I know that I total is equal to I1 plus I2. Well, what is I1 plus I2? It's going to be the change in V over R. So EMF over R1 plus EMF over R2. I can divide both sides by EMF, and I get I total over EMF equals 1 over R1 plus 1 over R2. And this is just the inverse of Ohm's law, right? Like instead of EMF over I, it's I over EMF. So that would be 1 over the equivalent resistance. So the equivalent resistor rule, right? It's the sum. Once again, I forgot the rule, but it's the sum of the inverse of the equivalent resistor is equal to the sum of the inverses of each individual resistor. So opposite from capacitors, you can kind of think about why. And as a kid, as a teachers say to act, I don't know, academic, I don't know. They always say like, oh, it's an exercise for you to try. So yeah, I'm gonna do it because I gotta keep these videos short. This is an exercise for you to think about why capacitors and resistors have opposite rules. Hint, hint. Think about the capacitance equation and this equation. Yeah, those are the rules. Let's see it in action, right? Let's get a combo circuit going, and let's try to find the I's and the V's and the P's for each value. So I'm gonna use different colors, I guess. Let's do that. Do we do that? It's fine. Okay, you know what? We're not gonna do different colors, but let me draw a circuit here. So we're gonna have a battery. We're gonna have one resistor here. We're gonna have another resistor here. We're gonna have a little 3 split. We're gonna have a little 3 split, and then we're gonna have another kind of split here. And these all connect back up to another resistor. And then boom, bada bing. Okay, little scuff drawing, but I'm trying to keep this quick. Let's say this is 21 ohms. Let's say this is 10 ohms. That's what I decided on, 10 ohms. Let's say this is 5? 5, 10, 10. Okay, 5 ohms, 10 ohms. 10 ohms, 20 ohms, 20 ohms. And let's say, I don't know, let's just pick a random number, 8/7 ohms. Let's say this is 70 volts. I don't have my calculator with me. Shoot. Okay, that's fine. That's actually a little bit annoying. But you'll see it's actually not too bad. So I want to find, this is going to be kind of crazy. I want to find the current. I want to find, we're going to do that. Let's do it. Why not? I want to find the current. I want to find the voltage across each resistor. And I want to find the current through each one. I want to find the power dissipated by each one. How would I go about doing that? Well, it helps to first find the equivalent resistance. Because I know the battery voltage, right? So if I can do change in V over R, or the EMF, right, of the total battery over R, I can find the total current. And then I can start thinking about, the total current passes through these three. I already knocked out a bunch. Then I can think about this nut jumbo and think about how the current splits. So to approach this, I got to think about, well, hey, how can I use my parallel and series rule, right? I can't use series with the 10 ohm and the 10 ohm because they're not in series, right? In order to be in series, the current, and I should have clarified this more. I talked about this in my Unit 10 video. They're not in series because the current here would not be the same as the current here, right? The current splits. So in our derivation, right, the current had to directly pass through one into the other for the current to be the same. This isn't the case, so current splits, they're not in series, right? The 10 ohm is not, believe it or not, it's not in parallel, this 10 ohm, with the 5 ohm because this 10 ohm right here does not have the same potential drop as the 5 ohm, right? The potential drop here is like, if this was 6 volts, it's if this was 6 volts and this was 0 volts, it would be like -6, right? It's -6 volts. I'm just imagining numbers. My point is, if this was 6, through the 10 ohms, it would only, after that, it would only be like 3 volts, because then it would have to go through this over here to get back to 0, right? They're not the same potential difference, right? They don't give the same potential difference. What does give the same potential difference, though, are these two 20 ohms, right? They are actually in parallel, right? You can see there, I think there's nodal analysis or something, but I think that's beyond the scope. Point is, they're in parallel because the potential drop here would equal the potential drop of the other one, right? So I can make this in series, so I'll just kind of like, expand this branch. I won't like draw the whole thing, but now I can combine these, and if I use, right, 1 over r equals 1 over 20 plus 1 over 20. If I plug it into my calculator and then take the inverse, remember, when you sum these up in your calculator, you then take the inverse, you get r is equal to 10 ohms. And that's a nice thing to remember, right? If you had two of the same resistor in parallel, it's going to be half the resistance, right? Because 1 over 20 plus 1 over 20, you get 2 over 20. When you take the inverse, it's 20 over 2. If you had 3, right, it would be 1 over 20 plus 1 over 20 plus 1 over 20. It would be 20 over 3. So that's actually a nice little convenient rule to have if they have the same resistance. So I have 10 ohms here, 10 ohms here, 10 and 5. The 2 10s, right, now they're in series because the current, it passes through each of them. So now this whole thing just becomes 20, right? Simple sum for the series, right? So now, oh boy, we have this nasty little parallel here. So 1 over r equals 1 over 5 plus 1 over 10 plus 1 over 20. If you do this in your calculator, you should get that r is equal to 27 ohms, right? Now you can see why I had this 8/7, right? So for this whole mumbo jumbo-ness, this whole thing, I don't know how I'm going to draw this. This whole thing can just be substituted in as one resistor with resistance 20 over 7 ohms. So 20 over 7, 8 over 7, 21, right? So 27 plus 8/7, that becomes 28 over 7, or just 4. So 4 ohms. 21 plus 4, that's 25, plus 10. This whole thing becomes 35 ohms. And I should use the eraser, but I want to make this quick. So then, boom, the total current is just 70 over 35. It's going to be 2 amps, right? So now I can actually figure out a lot of things with that, right? If I multiply 21 times 2, right, I get 42 volts, right? If I use V equals IR, this is a 42 volt potential drop. If I now do, if I do 10 times 2, this is 20 volts, right? 16, this is 16 over 7 volts of a drop right here, right? For this whole branch, I know the equivalent resistor is 20 over 7, so this would be 40 over 7 volt drop for this whole parallel branch. So that would include this element, that would include this element, and then that 40 over 7 volt also applies to that 20 ohm resistor that equivalates all three of those, right? So these get complicated. You got to keep it organized, but you can see that you can actually do it pretty quick, right? And then 40 over 7 volts, I can use Ohm's law to find the current. If I know that this whole thing is 40 over 7 volts, I can get the current is, divide that by 20, I get 2 over 7 amps. So if this is 2 over 7th, right, I can just do it like this. I can just work kind of backwards, right? Find the equivalent resistor and then work backwards, and then I can find the power too. So that's just a quick combo circuit example. I just wanted to show you. Now when we're gonna talk about, I want to talk about current density real quick. So if you had, let's say you had a weird resistor, and I'll actually talk about resistance in it. Let's talk about resistance first. So we talked about resistors, right? And resistors are kind of complicated, right? Like in real life, you can imagine. I don't even know how a resistor works, or like how a light bulb works, right? My guess is maybe they use like, I don't know. Maybe I'll look into it. Maybe it's like, no, it can't be. I was gonna say black body radiation, right? Like the current, it's so hot that it makes it glow. I don't know, maybe. But like LED lights, I don't really know how those work. I'm curious to learn how they work. That's kind of interesting. But very simple resistors can be, described as just any material that, just any material that kind of is uniform in area, right? It's like a cylinder. Or it could be any object. Any object could be a resistor. I could be a resistor. But in terms of like ohmic resistors that are easy to work with, yeah, like a cylinder will do, right? So if this has an area A and a length L, let's first think about this. Resistance, if I make the cylinder longer, you can imagine the resistance will be larger, right? Right? If you think about a poor electron or a poor, positive charge trying to go through a resistor, if that resistor is longer, it's going to be more of a journey, right? You're going to need a little bit more EMF to get you at the same pace as per usual. It has larger resistance, right? So larger resistance. If you have, now think about this, if you have a bigger area, well, hey, it's a little bit easier to go through, right? So I know resistance is, might be proportional to L in some way. Maybe it's like proportional to L squared, or maybe the root of L. I don't know, but I know as L gets big, so does R. And if the area gets bigger, well, it's going to be easier for the charge to move through, right? It's not as constrained. It can freely, take its space, go through that resistor. So I know it's going to be proportional to the inverse of area in some way, right? Maybe I don't know specifically, but, it's 1 over, I'll just say it's 1 over A for now. And, and hopefully, it makes more sense, right? If the area is really, really, really small, those charges, right, they're going to have to really squeeze their way through. The resistance is going to be bigger. Now, maybe you're in the lab, maybe you do some linearization and stuff, and you find out that, yeah, it is indeed proportional to L, like linearly, and it is just inversely proportional to area. Now, what's the other thing that might be missing, right? What else does a resistance depend on physically, right? Like physically, what does a resistor depend on? Well, maybe the material, right? Hey, a conductive material, right, probably won't have a resistance of 0, right? That would be kind of crazy. I think those do exist, superconductors, right? But something of like, a conductive material is going to be way less resistive. The charge is way more freely able to move that thing. Versus like an insulator, it's going to be very hard to move through that resistor. Now, materials have something we call a resistivity, right? That's like a physical property of the material that kind of tells us, I guess, how easy it is for electrons to move through that, or how hard it is for electrons to move through that material. Is it related to conductors and insulators? I think so, probably. I might be wrong on that. I might have to read up on that. But the equation for resistance ends up being rho, right? This is rho, L over A. So this is a nice little equation to know. I don't know how much you'll use it in my practice for this exam. I have not encountered an FRQ yet at all maybe one actually. There might have been one that asked us to use the slope to find the resistivity, right? So you would graph maybe L over A, for example, versus R. So you can have, it doesn't have to be uniform in area. You can have resistors that look like this, right? For something like this, you would actually have to integrate to find the total resistance, but I'm not gonna do that because I don't think they'll ask you to do that. But if you had current going through this thing, the current would still be constant, right? It's not going to be like, because it would be weird if current is more here, then there's a bigger voltage drop there, but that probably won't be the case. current will be the same, right? That's the rule you kind of established. Well, if the current's the same, you can imagine the current per area here will be larger than the current per area here, right? Because there's smaller area here, but there's more current per unit squared, right? There's the same current in a smaller area. We call this quantity current density. You might encounter some problems using J where you have to find current density. I haven't come across it in an FRQ before, but it's just something I'm going to put out there for you to think about. That is what current density is. All right, two more topics: Kirchhoff's laws, and then RC circuits. So Kirchhoff's laws. Let's actually. I'm just gonna get a circuit going here. We're just gonna get a crazy looking circuit. Oh wait, before that, actually, I want to talk about potential a bit more. So I'm gonna get a circuit here, and these are actually light bulbs. These little, how do I draw this thing like that? I don't know. I'll draw a little. Yeah, sure. That's my new symbol. A circle with a C. That's a light bulb. Actually, no, that looks too weird. All right, I'll just do dots, I guess. Circles with dots. Let's get a weird circuit like this. Now, let's say they're all light bulbs with the same resistance. Which one will burn the brightest and which one will burn the dimmest? Well, to figure that out, we got to look at power, right? Power is equal to I times V. So if you can get more power, you can dissipate energy at a faster rate, and you can get your bulb burning brighter. But thinking about current's a little weird, right? Like it's kind of hard to think about current, 'cause current changes. Like maybe more current will go here because of path of least resistance, which I'll talk about and kind of debunk ish. But it's kind of hard to think about in terms of that. So we can actually think about it in terms of like, we can use I squared times R, right? Because I know the resistance will be constant. So if I think about, well, which one is getting more current, I can think about it like that. Or I can think about it in terms of potential, right? Which one has a bigger potential drop? That one will have more power. Now, doing it in terms of current, it's a little hard, right? Because, well, shoot, right? It's like there will be current coming this way, right? And, will the charge, will there be current going this way? Will some of it go here? But I thought path of least resistance, right? Maybe the charge will go up, maybe it'll go down, and then how do I know which one's getting more current? It's a little bit harder to think about it like that. It's actually a little bit easier to think about in terms of potential, right? Let's think about it like this. Along this wire, the charge is at the highest potential it's going to be, right? Along this part of the wire, right? At the black. So, and then the lowest, we'll say, is going to be, do I have another color? Please? Let me have another. Okay, let's say the lowest is going to be blue. The lowest the potential or the charge will, or the lowest potential the charge will ever be at is blue, because then it jumps back up from the lowest to the highest thanks to the battery. So I can see, well, hey, this resistor is going from high to low. So that's the biggest potential drop that we're going to see, right? So that's going to have the most power. This one will be the brightest, right? And then we can look at, well, okay. We can look at, well, hey, Jesus Christ, where on earth are my markers? Okay, I'm gonna have to use red. Bear with me. This might get a little crazy. The charge here will be at a lower potential, but I know it's not gonna be the lowest potential, so it's not the same potential drop. I know these two, they have the same potential drop, so they'll burn the same brightness, but it'll be less bright than that charge. Or not than that light bulb. I don't know why I said charge. But hey, take a look at this. There's current coming in through this way. There's current going in through this way. So there's going to be more current, right? They're going to join up and it's going to go into this light bulb. And this one will have, therefore, a greater potential drop, right? Because it's V is equal to IR. So I know this one will be the second brightest. And then these last two will actually burn the dimmest. So you can use voltage to kind of analyze how power flows through a circuit. Or not power, how voltage kind of changes across a circuit. Oh, okay, what am I saying? You can use voltage to analyze brightness. There you go. That's all I needed to say. Kirchhoff's law. Let's just get a circuit going here and let's try to understand why Kirchhoff's law is even useful. Hey, I have a battery. Now this battery kind of stinks. It actually has internal resistance. The way batteries work, it's a chemistry thing that I don't fully understand yet. I'm taking AP chemistry next year, so maybe I will. Who knows? But batteries, they actually often have internal resistance, just based off how they work. It's a chemical reaction that goes off or something, and they will actually have internal resistance. And we notify that. I don't know why I said notify. We kind of distinguish that with like a resistor, and then we draw a little box around it to show that like the resistor is kind of like a part of the battery. But it uses, like you'll see in a second, it's no different from like a regular resistor. Okay, let's say this is 20 volts. I'm getting this from a textbook, I believe. I just don't know which one. I don't know the voltage. Let's call it EMF1. I don't know the voltage for this one. We'll call it EMF2. Note the polarity, right? This is positive, negative, positive, negative. Let's say this is 1 ohm. They all have 1 ohm of internal resistance. Let's say this resistor has 6 ohms of resistance. Let's say this one is 4 ohms. Let's say this one is 2 ohms. Let's say there's 1 amp of current going down this way. And let's say there's 1 amp, 2 amps going across down like that. This, you can't really use your resistor rules, right? You have multiple batteries. How do I even approach this problem? Well, you got to use Kirchhoff's law. So Kirchhoff's law, Kirchhoff's first law, his voltage law. This guy's pretty clever. He realized that, hey, the change in V around a loop of closed wire equals 0. Always. This is pretty simple to understand with a simple circuit, right? The change in V here is the EMF minus the voltage across the resistor. It's really just IR, right? Needs to equal 0. It has to be by conservation of energy, right? Potential here, charge here, it'll go up, right? It'll kind of go up, and then it'll go down the same amount by the resistor to get back to where it initially started. So the change in V around that loop, that closed loop, is equal to 0. But the crazy thing is, you can apply this for any loop, right? You can actually apply this for this main loop, for this main loop of wire, and the top loop of wire, as long as it's a closed loop of wire. Now, the second rule tells us that the total charge coming into a junction. Wow, nice, Krish. I said function. The charge coming into a junction equals the charge coming out of that junction. So a junction is just where 3 pieces of wire meet, right? This is not a junction, right? This is just where 2 pieces of wire meet, right? So it's where 3. So 1, 2, 3. So the current coming into the function, right now it's 1 amp, and the current coming out is 2 amps. So the current coming in needs to equal the current coming out. So we kind of use these ideas, right? We use these 2 ideas, right? Conservation of energy and conservation of charge, right? This would have to be 1 amp. And then, I gotta find, let's try to find EMF1 and EMF2, right? Using loop rule. And remember, 1 amp plus 1 amp is equal to 2 amp. So the first loop we can use is actually the top loop, right? You can use there's 3 loops and 2 unknowns. So that means we have 3 equations. We have 3 equations and 2 unknowns. So you can solve that, system of equations pretty easily. Let's just start with this top loop, right? I know current, right, is coming through in 1 amp this way. So let's think about the change in loop, right? I'm going up this battery, or I'm going up a potential, so plus 20 volts. I'm gonna do the IR stuff in my head. I want to make this a little bit quick, but 1 amp times 1 ohm, that's gonna be minus 1 volt that is dropped. And then this is a little bit crazy, right? We're going backwards a resistor. If I go through a resistor normally, my potential drops. If I'm going backwards, my potential goes up. So that's actually a neat trick. I also still need to like understand why we can do that. Besides just being like a mathematical trick that just makes sense, right? You're going backwards, so you're going up the potential, right? Instead of forwards. So you're going up potential, so I'm going plus 4 volts, right? 4 ohms times 1 amp. And I'm still using the 1 amp here, right? If this was 2 amps, it would be plus, I wrote a minus, it would be plus 8, right? So just remember that. I'm going up the internal resistance, so I'm gonna go plus 1 volt. And then now batteries, if I go forward, it takes me up. So if I go backwards, they take me down. So I'm going minus EMF1 equals 0. So I get EMF1, if I add it to the 0 side, right? Whole change in V needs to equal 0. 20 minus 1 is 19, plus 1 is 20 again. Wait, I messed this up. Right, didn't I? Wait, I did mess this up. How did I mess this up? Oh, I forgot. I forgot. I also have to go back. I'm so sorry. I need to go back to my 6 ohm. So then minus 6 volts, right, equals 0. So I get EMF1 equals 20 minus the minus 1 plus 1 cancels out. So I get plus 4 minus 6 is minus 2. 20 minus 2 is 18 volts. This is an 18 volt battery. You can use a calculator, obviously. Go nuts with the calculator. I'm just doing this in my head to save time. Woo! Let's go through this bottom loop now. So I know EMF1 is now 18 volts. So I can actually do this loop right here, right? So I'm going to start here, right? I'll start my loop here and end it there. So I'm going plus 18 volts, minus 1 volt, right? Thanks to internal resistance. Minus 4 volts, thanks to just resistance. Now this is a little crazy. Now, I'm not really going backwards in my loop. I'm actually going with the current, right? I'm going with the direction of the current. So I'm actually going down 2 times 1 is 2 volts. I'm going down 2 volts thanks to internal resistance, but I'm actually still going down the battery voltage, right? I'm actually going down because I'm going backwards. I'm going from positive to negative. That's a negative potential drop. Now, that's weird though. You have 2 batteries that are trying to push, like the positive side, they're trying to push each this way. Why is EMF2, why is current, going through EMF2? Well, the voltage, and I guess there's 2, right? The 20 volt and the 18 volt, they're able to provide bigger voltages, bigger pushes, right? Bigger electromotive force. I don't think I explained what EMF is. EMF stands for electromotive force. Voltage is not a force, but you can kind of think of it as one, because those 20 and 18 volt batteries are trying to push, right? Trying to push the charge through this EMF2. And this EMF2, right? This battery is trying to push back, right? Like, hey, charge, go this way. But it's not strong enough. So the charge, in essence, has enough energy to go through the other battery. And I think you can think about the chemistry more, but whatever. Minus 2 volts. Minus 4 volts for the other resistor equals 0. So I get EMF2 is going to equal 18 minus 1, that's 17, minus 4, that's 13, minus 2, that's 11, minus 4, that's 7 volts. So this is a 7 volt battery. So this is just a quick example of how you can use Kirchhoff's law. Now let's end this video with RC circuits. So you can charge a capacitor. We talked on the last video that, hey, capacitors charge basically instantaneously because there's no resistance, right? Like it just all the charge charges it up, all the charge, gets it back. It's instantaneous charging. Well, if you add a resistor, the resistor actually provides an initial set current. Without a resistor, it's infinite current, and that capacitor just charges instantly. But with the resistor, now there is some resistance. So this capacitor will take time to charge. Now, how can you find out how long it'll take it to charge? Well, you actually can't. It'll actually take an infinite amount of time. Here's why. You can use a differential equation. So I know thanks to loop rule, the total across this loop is going to equal 0. So the EMF minus the resistance, so minus I times R, minus Q over C, right? Remember, we're back to capacitor. C is equal to Q over V. So I know V is equal to Q over C. So the battery voltage minus the voltage drop to the resistor minus the voltage drop to the capacitor, EMF minus IR minus Q over C. It's going to equal 0. Now, current is really just dQ dt. Well, hey, I have a dQ dt and a Q. This is actually a differential equation. The charge on this capacitor will change over time, and by solving this differential equation, we can actually get the charge as a function of time. I'm not going to go through the steps because I want to save time, but I've made videos. There are countless of videos. And this is, if you know calculus, this is not a terrible differential equation. If you're in Calc BC, you could do this. If you're in Calc AB, you could give it enough thought and you can do this, I think. I don't know. You solve this differential equation, you get that charge is equal to the charge as a function of time is going to equal the EMF times the capacitance of your circuit times 1 minus e to the negative t over RC. If you take the derivative of this, you get the current as a function of time, which is going to actually just equal EMF over R times e to the negative t over RC. So let's graph this, right? If you have charge as a function of time, the graph, right? Let's think about it. When t is equal to 0, you get this e, well, it's e to the 0, which equals 1. So 1 minus 1, that equals 0. The charge on the capacitor is equal to 0, and I didn't even need to explain that because that makes sense. When I first plug in my battery to this whole thing, there's no charge on this capacitor. And then it charges exponentially, and it'll look like this. And it asymptotes. And it asymptotes at a certain value, right? Take the limit as t approaches infinity. E to the negative infinity is equal to 0. So you get 1 minus 0. That's just 1. 1 times EMF times C. What's EMF times C? Well, hey, that's just the max charge. Because one at most, this can have the voltage of the battery, right? So if this has the voltage of the battery times the capacitance, that gives us the max charge Q max. So this asymptotes at C EMF, which equals Q max. Well, hey, if I graph current versus time, then I get a decay function. This is just a traditional decay function, right? Where EMF over R, that's our initial current. Well, that's just the max current you get worth, right? Because when this is a capacitor, when it's not charged, it acts like a wire, right? Charge can just very easily pass through this, so the total voltage divided by the total R, that just gives us the initial current, and then it decays like so. So yeah, that makes sense. When the current is 0 after t equals infinity, the current is 0. That means the voltage across this thing is 0. So EMF minus 0 minus V cap, capacitor equals 0. Well, that means the EMF is, well, the capacitor voltage is the EMF, right? Because there's no more voltage drop by that resistor. So this actually all makes sense, right? Because when the current is 0, the capacitor is fully charged at Q max, physics works, right? Everything's consistent with each other. And good thing to note is something called a time constant. So tau actually is equal to R times C. Why is this a useful number? Well, if you plug in R times C into T, right, you get RC over RC, that's just 1. So you get E to the negative 1. And E to the negative 1 is roughly 0.37. So if you do 1 minus 0.37, you get 0.63. So you get 0.63 times the max charge. So the time constant actually tells us how much time it takes for our capacitor to be 63% charged. Yeah. Or, in terms of current, it tells us when it's going to be kind of 63% less. Because if I plug in tau here, RC, I get e to the negative 1, which is 0.37. So it's going to be 0.37 times as much as the initial current. That's the same as if the current had reduced by 63%. So that's a charging a capacitor. You can do a very similar process for discharging a capacitor, right? If you're discharging a capacitor, let's say the capacitor is charged like so. Right? You would solve a very similar differential equation where change in V needs to equal 0 across the loop. And I'm sorry, it's kind of getting dark in here. Let me just check my phone. Yeah, it's probably visible, but oh my god, this is a 51-minute long video. Okay, that's kind of a problem. Change in V across the loop needs to equal 0. So, V capacitor minus VR equals 0. So this will actually be Q over C plus dQ dt. Because dQ dt actually ends up being negative because less and less charge is going across that resistor. So when you solve this differential equation, you get Q as a function of T equals Q max, right? Or this could also be EMF times C times e to the negative T over RC. So it's a decay function, right? It naturally loses charge. Woo! Okay, that's RC circuits. Remember tau, right? If I plug in RC here, I get e to the negative 1, which is 0.37. That's, essentially the same as the, 0.37 times the initial charge. Well, that's the charge having reduced by 63%. So let's talk about steady state circuits, and I'm going to end this video after this because Jesus Christ, I was not expecting it to be that much. Hey, I have a 100 volt battery. And I have capacitors, and I don't know the capacitance, but I do know the resistance of these resistors. I actually have an ammeter. An ammeter is a device that measures charge. A voltmeter is a device that measures voltage across 2 points. So that's important to know. So let's say I have a switch. Let's give these some numbers too. Oh my god, 25 ohms, 75 ohms, 50 ohms, 15 ohms, and 25 ohms, and let's say this is 25 ohms as well. Let's say I initially close the circuit. What's the initial current reading? Well, capacitors initially they act as wires. So if as charge goes up here, it'll go through the capacitor instead of the resistor because it's less. It has zero resistance, right? It'll pick the path of least resistance. But really, that just means that the voltage across this initially is 0. So the voltage across this resistor needs to also be 0 because they're in parallel. So, all the current will just go through this capacitor. So the current will for sure go through the 75 ohms and it will for sure go through the 50 ohms, right? Because this path has resistance and so does this path, right? At the end, the charge will go through this capacitor, skip this resistor, but it will go through this resistor. Current will go through this resistor as well, therefore, right? So they have a potential drop, and then it goes through the 15 ohm resistor. Whew! So the initial resistance of this circuit is going to be 20, or not 25 ohms, right? Because it doesn't go through the 25 ohm resistor, but it's going to equal 75 ohms plus. So now we have a 25 ohm, right? Because it skips this resistor, but it does go through this resistor. You have 25 ohm plus 50 ohm, but that's in parallel. So that'll be roughly 16.67 ohms plus 15 ohms. If you do the math, 31. That should be, I don't know, 5.667. I think that seemed right. I think that is right. I'm gonna calculator check. It'll be, I think it actually might be 101. I don't know. Dude, plug this in your calculator, and then you do 100 divided by R initial to give you the current initial. The answer, if you go ahead and solve it, it's like 0.9375 amps for the initial. Now, for the final current, after a very long time, right? Because we know capacitors won't fully charge, but after a long time, they're essentially charged. After a very long time, the capacitors are fully charged, so they act as kind of open switches, right? No current will pass through them because they're fully charged, right? No more additional positive charge can go onto the plate and knock off another positive on the other side. They're fully charged. So then I don't even have to really, actually what happens is, well, 25 ohm, all the current goes through, then 75 ohm. But now, none of the current goes through this capacitor. It just goes through this branch, this series branch. But no more current will go through this branch because this capacitor acts like an open wire. So no, this doesn't complete the circuit. No more charge will go through that branch. So I really get the R final, or R is T equals infinity. It's going to equal 25 ohms plus 75 ohms plus 25 plus 25, right? I'm summing these up because they're all in series, plus 15. You can add that up, do 100 divided by the resistance, and you'll get the final current after a long time. So yeah, I did not want this video to be long. In fact, I actually wanted this to be one of my shorter videos, but circuits are just, there's a lot to it. So there you go.